Well, AI winning a physics prize. That's a new one. You don't see that every day. Color me surprised when the Nobel Prize in Physics went to a couple of AI pioneers.
It definitely turned some heads. I mean, we usually think black holes and quantum mechanics, right? Not artificial intelligence.
Exactly. But this year, it's all about machine learning with John Hopfield and Geoffrey Hinton. And get this, they used physics to do it. It sounds like our kind of deep dive. What do you have for us?
Oh, tons. You sent over some really interesting stuff, like those articles from New Scientist and Science News, plus all that background from the Nobel Committee. Let's dive right in with John Hopfield and his claim to fame, the Hopfield network. He developed it back in '82.
82, wow. So is it self-driving cars back then?
Huh. Not quite, but definitely ahead of its time. The funny thing is, Hopfield wasn't a computer science guy, you know? He was at Princeton, deep into molecular biology, the theoretical stuff.
Well, hold on, molecular biology, that's a long way from AI. How do you make that jump?
Well, it all started with a neuroscience conference. Hopfield was blown away by the brain, how all those neurons work. Got him thinking about neural networks in a whole new way.
So he wasn't just looking at individual neurons, he was looking at how they all work together.
Exactly. He realized that those neurons, working as a system, were way more powerful than just looking at one at a time. Kind of like how a single grain of sand isn't much, but you put a bunch together, you've got a beach.
Okay, I see where you're going with this. And that's where the physics comes in, right? Something about magnetism being a big influence.
You got it. Hopfield made this brilliant connection between how magnets act and how his networks could learn. Imagine those little magnets like the ones you stick on the fridge. They can point up or down, just like a switch being on or off.
And that's like the ones and A's and computers use, right?
Exactly. Binary code. Just like those magnets, each point in a Hopfield network has a value it can flip. And here's the physics part. Physicists can actually calculate the energy of a magnet system based on how all those tiny magnets are arranged. And Hopfield, he figured out how to do that with his network.
Wait, back up. Energy in a network. How does that even...
Okay, picture this. A bumpy landscape, hills and valleys. Right. The valleys are low energy, things are stable there. But the hills, that's high energy, more chaotic.
So like a ball would naturally roll down into a valley, looking for that low energy spot.
You got it. And in a Hopfield network, the connections between those neuron-like points, they're adjusted as it learns. It's like reshaping those hills and valleys on our landscape. As it processes data, it's trying to find the configuration, like the arrangement of those little magnets that minimizes its energy, just like that ball rolling downhill.
So it learns by finding the most stable state, the lowest energy point.
You're getting it. And that lowest energy, it represents the stored pattern that best matches the data it's been fed. Like it learned to associate patterns with those comfy low-energy valleys. Pretty neat, right?
That's seriously clever. So it has its own little memory bank of patterns, and it's always looking for the closest match. Never thought of AI working like that.
And get this, it could store multiple patterns at once, each one tucked away in its own little valley on that energy landscape. Showing the network something new, it's like giving that ball a nudge. It rolls down into the nearest valley, revealing the stored pattern it's closest to. Back in '82, this was a big deal.
No kidding. So what could it actually DO back then?
Well, think about how we recognize faces, right? Even with a hat, different hairstyle. Our brains are good at seeing past those changes to the underlying person. Hopfield's network, it was a big step toward getting computers to think a little bit more like that, recognizing those patterns, even when the input was fuzzy or incomplete.
That's wild. So mimicking magnetism revolutionized machine learning.
Totally changed the game. But hold on, because it doesn't end there. This is where Geoffrey Hinton enters the picture. He looked at Hopfield's work and thought, we can take this even further. And he did, in some truly mind-bending ways.
Oh, can't wait to hear about this. I read something about Boltzmann machines and statistical physics. Now we're really going deep.
Oh yeah, we're diving into the deep end now, but trust me, it's worth it. Hinton's insights into how machines learn were about to get even more extraordinary. So we're talking about Hopfield's network, mimicking magnets and finding the lowest energy state to learn. Remember?
Yeah, like finding those valleys in a bumpy landscape. Pretty cool way to picture it.
Well, Hinton, he took that idea and just ran with it. He was obsessed with machines learning more like we do, you know, not just programmed, but experiencing and figuring things out.
Right, like how we learn what a cat is. Nobody gives us a cat manual. We just see enough of them and our brains, boom, they get it.
Exactly. And Hinton's thinking was, why not machines too? He and his colleague, this guy Terence Sojnowski, they looked at Hopfield's network and saw a way to make it even more powerful, more organic, by bringing in statistical physics.
Statistical physics. Okay, now you're just using big words to sound smart. Do I need a physics degree for this?
Nah, not at all. Think of it like this. It's about understanding systems where there are tons of parts interacting. Like imagine a room full of bouncy balls all bouncing around, hitting each other. Impossible to track every single one, right?
Yeah, you'd go cross-eyed.
Exactly. But you can still figure out things about the whole system, the average speed of the balls, how much pressure they're creating. That's statistical physics.
So big picture stuff, not sweating the small details.
Bingo. And that's what Hinton did. Instead of just individual nodes and connections like we were talking about with those bouncy balls, he treated the whole network as this statistical system.
Yeah.
Totally new way of thinking about learning.
Okay, I think I'm following. But how do you use this?
He invented the Boltzmann machine. It builds on Hopfield's work, but adds this really cool thing, hidden nodes, called that, because they don't get info directly from the outside.
Hidden nodes. So what do they do then if they're not getting info?
That's the cool part. They're like the network's internal detectives, processing behind the scenes, looking for patterns, relationships, stuff the visible nodes might miss. Like they're solving a mystery.
So if the visible nodes are like our eyes taking it all in,
Mhm.
the hidden ones are like our brains trying to make sense of it.
Perfect analogy. And just like our brains don't show us everything going on, and there are these hidden nodes, they do their thing in the background. But here's the key. This whole process, it's driven by probabilities, that statistical physics we were talking about.
Probabilities. Not finding the absolute right answer every time, but the most likely one.
You got it. It's like the network saying, based on everything I've seen, this is the most likely explanation. And the amazing part is, Hinton figured out how to mathematically represent all those probabilities, all those possible states, using the Boltzmann distribution. It's a mouthful, but that's the secret sauce.
Secret sauce. I like it. So instead of memorizing specific things, this Boltzmann machine is learning the patterns, the rules of whatever it's seeing.
Nailed it. And being able to generalize like that, that's what makes it so powerful. Means the network could see a brand new cat picture never seen before and still know it's a cat. Not because it's memorized every cat pic out there, but because it's learned what makes a cat a cat.
That's incredible. So we went from magnets and landscapes with Hopfield to this whole statistical physics hidden node world with Hinton. These guys were on another level.
For sure. And it had a huge impact. Think about those massive neural networks we hear about now. Tons of layers processing crazy amounts of data. Hinton's work was a key step in that direction. He didn't just have the ideas, he found ways to actually make them work, build bigger, more powerful networks.
So Boltzmann machines, as revolutionary as they were just the start.
Exactly, like the prototype for the whole AI explosion we're seeing today. And a big part of that explosion was realizing that to train these super complex networks, you need one crucial thing, data, and lots of it.
Data, huh? Like all those cat pics, articles, everything we're feeding these AI systems. It's like they're food or something.
Perfect way to put it. Data is the fuel that makes these massive networks go.
It's crazy, right? The amount of data we're talking about, every purchase, even just walking around with our phones, it's kind of overwhelming.
Totally a data-driven world now. And it's that explosion of data that's really let deep learning take off. Think about it. To train a network with millions, even billions of connections, you need a ton of examples. Like teaching a kid to read, right? You can't just show them the alphabet once and expect them to write a novel.
Right, they need tons of books, just like these AI systems need mountains of data.
Exactly. And now we finally have both. We've got the data A&D, the computing power to handle it. That's why we're seeing these insane AI breakthroughs now. Like all the puzzle pieces are clicking into place.
And it's not just cat pictures anymore. I mean, these AI systems are doing some seriously impressive stuff. In all kinds of fields. I was reading the Nobel Prize stuff you sent over. They're using it to discover new particles, find distant planets, even to figure out how proteins fold. That's wild.
It's mind-blowing how AI is changing science. Like in particle physics, they're using it to go through tons of data from those particle colliders, looking for the tiniest hint of new particles. It's like finding a needle in a haystack the size of a planet.
Wow, that's a lot of hay. So it's like having this super-powered research assistant, one that can analyze data way faster and more accurately than any human ever could.
Exactly. AI is freeing up scientists to focus on the big questions, the creative stuff, while these AI systems do the heavy lifting. It's a crazy, powerful partnership.
This has been an incredible look at AI. We've gone from magnets and landscapes to hidden nodes and statistical physics. Who knew AI had such deep roots in physics?
It's been a wild ride for sure. And the best part, we're just getting started. AI is constantly evolving. What seems revolutionary today might be old news tomorrow.
It really makes you wonder what the future holds for AI. What amazing discoveries are right around the corner. I guess we'll have to wait and see. Thanks for joining us, and be sure to tune in next time when we take a deep dive into another exciting scientific topic.